Video lesson 10.1, intro to exponential functions. So let's look at the do now first, and let's refresh our memories on sequences. So this first sequence that we have here, is it arithmetic or geometric? And in this one, it is geometric. The reason for that being that it is not a constant change, right? That is growing like as a linear function. It is something that is growing, it's being multiplied. So like 1 times 5 is 5, 5 times 5 is 25, 5 times 5 times 5 is 125, and so on and so forth. So this one is in fact geometric. All right, let's go back to that thought process and actually make the explicit formula when dealing with this one. So that's going to be a sub n is equal to a sub 1 times r raised to the n minus 1. Right, so this means like any term when dealing with the first. So in this sequence, we've got 1 as our first one. We're increasing at a common ratio of 5. And we have this case n minus 1 for whatever number or in the sequence we are looking for. So that would be the specific one in this function. So if we were to make these, like if we were like to plot them, right? If we were to plug these in, if I plugged 1 in, right, for here, I'm going to get 1 as a result. If I plugged 2 in, right, our second term, we would get 5. 3 would be 25. 4 would be 125. And again, I'm just looking here, first term, second term, third term, fourth term, right? Or we could have plugged them into the formula, but we have them in there. But the last one is 5. We don't have that one, so I would have to plug this one in. Or if you pay attention to see what the sequences is, this is just going to be this times 5. So that's just going to be, what's that, 625 for that one. So if I went and actually plotted these, right, on here, so you got, this is going up by a lot here, but so we'd have like 1, 1 would be like right here, right? 2, 5, 3, 25, 4, 125, that's up here somewhere. 5 is, we just said 625, that's gonna be all the way up here. So as you can see in this one here, as this goes, it's slowly increasing, and then all of a sudden it ramps up dramatically and goes up quickly from there. So that's the importance to notice about this function, this geometric function. It has an exponential growth here. It's an exponential function. It starts off slowly growing, and then it wraps up and grows really quickly eventually. So that's an important thing to notice with geometric functions. They are exponential functions in this case. So when dealing with exponential functions, we can write them in this format. F of x is equal to a times b to the x, where a and b are not 0, and where b is greater than 0 here as well. X can be any real number. That's just going to be the exponent value. And b is the base, right? B is the base, and it's a constant, all right? The x is the exponent. From there. So in this case, right, for here, when we have these types, A represents our y-intercept. All right, so where it crosses the y-axis, A term. B represents the rate, right? In this case, the common ratio. Okay, from there. So y-intercept, or it also is referred to sometimes as the, when dealing with exponential, that would be initial interval. It's another term that you hear a lot. That is the where it's going to start, where the function's starting, and then the common ratio is the process. Should have put rate here, not ratio. It's the rate, which is the common ratio. All right. For here, notice here, the graph does not have a constant rate of change, right? It's not constant, right? If it was constant, then we'd be linear, right? But it does have a constant ratio. right? So each time it is increasing, it's increasing by, in this case, in this previous example, as a multiple of 5 in the do now question. All right, from here. So that is the essence of a exponential function, and we do need to pay attention to what an asymptote is. All right, from here. So an asymptote is a line that the function gets closer and closer and closer to, but never actually crosses or touches it, right? So it's approaching it, but it never actually gets there, right? So in this example here, we've got an asymptote at the y equals 0 line, aka the x-axis, right? This is approaching that, but never actually gets to it, right? I can't raise something, a number to an exponent and get 0 out. It's got to be something that it's always going to be a positive answer. I can never get a negative either. So it's always approaching this, but it never actually reaches it. All right. From here. So the important thing to kind of pay attention to with exponential functions is that they have two variations. You have a growth and a decay, right? And they are, each one of them, whether it's a growth or decay, is growing or decaying at a constant rate of change, right? A constant ratio, right? That common ratio doesn't change throughout the function, right? So if it's an increasing percent, right, then I have the b value being greater than 1, and that means we're going to have a growth, right, from there. So that means that the function, as the b gets, if it's larger than 1, that means as the x gets larger, it increases more and more rapidly. So just like the one we did in the do now, like this function here starts off slowly growing, and then as x gets larger, it rapidly increases as it goes. Okay, but that's the growth portion of it. If the b value is less than 1 but bigger than 0, because we can't have it less than 0, then we're going to have a decay. All right, and that just is the opposite. That means that it's decreasing, right? First rapidly, and then it's kind of tapering off. So in this example here, we still have our asymptote here at the x-axis. It's getting closer and closer and closer and closer to it, but it's never actually getting there. But it's rapidly decreasing and then slowly decreasing as we get further and further along here. Okay. So those are the characteristics of exponential growth and decay functions that are important to know. And just knowing some of those characteristics allows you to kind of answer a lot of these questions sometimes without much work. Right? Look at example number 1 for this one. A population that initially has 20 birds approximately doubles every 10 years. So we have a doubling aspect. That does not mean, that's a constant ratio here, right? Right? That means that it's not a constant rate. It's not like each year, the same amount is being added, right? It's changing over time. So right away, once I see this, the first thing I notice is that at this situation, right, we have a common ratio, which means exponential function, right? So looking at my answer choices, I'm going to eliminate one of these immediately, and that would be here. Actually, I have these backwards. Number 4, right? Because this is linear, right? That's a linear function there. So right off the bat, I can say for sure that this one is not going to work because, again, this is just a linear function. So it can't be that. From there. So now I'm going to look at the other ones and look at their characteristics. Again, we know that it has an initial count of 20, right? So that means we're starting off at 20, which in this first example, it's starting off at 0, so that one's out. And then 2, and what should be 3 here, but 2 and 3, they are both starting at 20. but one's increasing, one's decreasing. So if I'm doubling every 10 years, right, that means that I am growing. So therefore, this one cannot be the correct answer. It would not be a decay, it would be a growth, and therefore option 2 is the correct answer that best represents this situation. So again, there's no math to do there, so to speak. It's just understanding the characteristics of the functions and the exponential growth and decay concept. And you can do basically like a process of elimination to kind of answer those types of questions. All right, for example number 2 here, let's actually create the information. We want to identify the initial value, state whether the formula models an exponential growth or a decay, and kind of go from there. So let's look at the pieces individually. So first off, let's think back for one moment to what we wrote at the beginning. A is equal to A times B to the X power, right? So the function is in this format. So instead of Y, they have it in function notation. That's fine. All right, so my A is 2 then. My B, in this case, is 2/5. So again, if I'm going to say if this value, right, if B is greater than 1, then it's a growth. If B is less than 1 but bigger than 0, then it's a decay. So in this scenario, 2/5 is less than 1. So therefore, it's a decay because B is less than 1. All right. Be careful. Looking at the second one, right? We have A is equal to 1, right? No, there's an imaginary 1 right in front of that, right? We don't have to write it. B is equal to 5/3. So is this a growth or a decay? Now, a lot of students do one thing here and then get themselves into a little bit of hot water with it. And it's a silly mistake, and it's a common one. And that is, don't say to yourself, oh, it's a fraction. B is a fraction. It must be a decay. Because just because it's a fraction does not mean that it's less than 1. If it's a proper fraction, it will be less than 1, aka the numerator is smaller than the denominator. It will be less than 1. But if the numerator is larger than the denominator, you have an improper fraction, which represents something bigger than 1. So in this case, B is larger than 1, therefore it's a growth in this case. Okay, so do be careful with that. It is a common mistake, just saying, oh, it's a fraction, and then jumping to decay. So you got to pay attention to the fraction itself. Okay. All right, example 3. So let's look at what we have here. 3 functions are shown. So I've got 3 different functions going on. We got h of x, g of x, and f of x. Which statement is true? So we kind of have to go through each one of these and kind of determine whether the information is correct or not, and then, process them and then see which one works. So it says here, the y-intercept for h of k is greater than the y-intercept for f of x. Well, h of k's y-intercept, right, where it crosses, is here. And that would be over here, this information. So that is not correct. This intercept is not larger than that one. That one's out. We've got the y-intercept of f of x is greater than g of x. So if we look over here, when is x equal to 0? If I plug that in, I'm going to get 3 to the 0 plus 2, which anything raised to the 0 power is 1. So that would be 3. So f of x intercept is not greater than g of x, so that one's out. Y-intercept h of x is greater than y-intercept of both g of x and f of x. Well, that one is also clearly wrong. And therefore, this should be our answer. The y-intercept of g of x is greater than f of x and g of x. F of x and h of x, which is true, making option 4 the correct answer. So again, not a lot of work here. There's really not much math. I mean, yes, I had to plug in here to find this value, but Otherwise, it's just kind of interpreting the information from the your knowledge of the exponential functions. All right, so for example number 4, let's actually take the time to try and create a equation here for this specific one. So again, my function y is equal to a times b raised to the x. All right, I'm looking for here. Now, the problem here is I don't know what that value is. It's not a nice number that crosses nicely, so I don't have that number. So I got to get a little fancy. I got to plug in and try and figure out what that is. So let's pick points that we can see here for sure. So I've got, looks like I've got 2, 1 is 1 point, and 3, that one's fine too. I'm just going to pick this one. I looked at this one next, so I'm going to pick 4, 4. But we could have used the 3. That's fine. But either one doesn't matter. Could have went over here to a 5. Looks like 5 and 8. Could have used that one as well. Again, any 2 points would work here. All right. So I want to kind of work and figure out what this is going to be. So take the situation. So if I want to figure out what A is, right? So I'm looking for what A's value is. Take this and plug this in. So I'm going to plug in my values here, right? For here. What's happening? Now, what's happening with my growth, right? Figure out the B value first. So what's B? So B goes from 1 to 2 to 4 to 8. So B ends up being 2, right? We're increasing at a rate of common ratio here of 2. Each value gets doubled as we go. So if I take those values, I pick one of these points. It doesn't really matter. I'll pick this one, right? Let's plug that into the formula. Along with B is 2. And now I have an X, a Y, and a B, leaving me with just A. And that's something we can solve for. So here, so we'll do 1 equals, A is what we're looking for. B we'll say is the 2. And X we had as, it was also 2 from there, right? So simplify this. We've got 1 is equal to A, 2 to the second power is 4. If I divide that, I'll get A alone. So A is equal to 1/4. Now I have an A, and I already found the B. So now I can say for sure that this function is y is equal to 1/4 2 raised to the x. And then I would have an equation that represents this function from the graph. Again, they can give you points. They might give you the B value. They didn't in this case. We could figure it out. So you just gotta have to go through each piece and figure out which ones you have, what you need, and then work backwards to find the parts that you're missing. All right, rewriting the formulas is also very key helpful process in trying to solve some of these because, again, using my exponent rules allows me to kind of shortcut a lot of times. So it says which one of these is equivalent to the function p of t. So at first glance, I look at them. Not an easy look, but if I rewrite this, then this might now also become a little bit easier to see. So let's rewrite this. So it's 300 times. I have an exponent with 2 things, right? The exponent has its 4t. So I could break that up because in my exponent rules, right, if we have, and I'll just do this off to the side here, over here. So if I have like a to the x, times a to the y, right, with this part here, the information that we allowed us to do is I can, break these apart from those. So I can rewrite this as a different thought process. I can reword, so to speak, the function, and allows me to kind of make my life a little bit easier and say, well, what would this be from there? So if I think of this, right, as, just 2 to the 4th for a minute, that would be 16, right? So I could rewrite this part as 2 to the 4th, aka to the t. So like 2 to the 4th to the t, right? Because again, power rule says that if I have an exponent raised to an exponent, I can multiply them. So if I rewrite this, right, 16 is this. So now I have 2 to the 4th raised to the t, which can be rewritten as 300. Let me just get this out of the way so it doesn't confuse you. All right. Instead of 2 to the 4th, we can make that 16, and then it's raised to the t. So I've got here an answer choice which looks like 2 that represents that scenario. All right. So again, that little trick using, in this case, the power rule, right, allows us to kind of manipulate it. Same thing happens here. Looking at this one here, I've got which one of these is equivalent to c of t. So with this information here, again, I have an exponent, 24 raised to the t. So I can take the base, so in this case, 1.029, right? I can say that that's raised to the 24th and that the whole thing was raised to the t, right? So now if I actually plug that into the calculator, so I don't know that one off the top of my head, so we've got 1.029 raised to the 24th. That gives us this decimal, which we will approximate here, 1.985. That one. That's 1.985. And we can look at that as being raised to the t, right? Because that was all of this, right? So now I have that portion, right, from there. And it was originally multiplied by 10, so now 10's on the outside. And c of t would equal all of this. So which one of these looks like that? The correct answer would be C. From here, oh, well, did I write that wrong? Oh yeah, sorry, this would have rounded off to be a 6, so that should have been a 6. So there we got 1.986 raised to the t is an equivalent variation of that. And again, both these examples just simply use the power rule to kind of help you solve those. So take an opportunity, re-look over the video on some of these problems. Don't be afraid to go back and look it over in more depth if you need. And don't forget to use the practice problems for better understanding.